Jaidev. So thanks for the invitation, first of all, to speak in this. It was, I guess, supposed to happen a long time ago. Anyway, it's a pleasure to give. Yeah, so I looked at various other topics. As far as I can see, this is somewhat disjoint from the others. Disjoint not in the sense of unrelated, but I mean, hopefully there will be something new for some of you at least. I have this plan, graphs and matrices, so I will explain. So it's meant to be understandable, first of all, nothing very sophisticated, but very important actually. It is some deep stuff, but with very elementary considerations in a way. Anyway, whatever be my plan, I would like if people can interact, unmute themselves, ask questions, so that I know whether or not I'm making any sense. It is not so important I tell whatever I plan to, but it is more important that people get something out of it. To all the parties, so is it true that participants can unmute themselves at any time? Hello?
Yes, sir, we can.
You can, okay. So please do feel free to unmute yourself, ask questions, stop me if you want me to repeat something. I give it more like a board lecture, so let's see. So there is no power here, so you may not see me, but it's not needed to understand the material. Okay. So let me kind of start. So what is graph? So I think many of you may be familiar with the notion of a graph. Okay. Oh. Okay, so the first notion I want to introduce, okay, where is the pen? Yeah, is that of a graph. Oh, have I shared it? Actually, maybe I have not shared it actually. So hold on. So I can share the OneNote or I can share the screen, which works better. I guess maybe I can just share the screen itself. Okay, do you now see my this OneNote?
Yes, sir.
You see this, right? So suppose I move here. Do you see this also?
Yes, sir.
Okay. In that case, okay, let me start with my OneNote. This OneNote can be shared later. Okay, so you will have a copy of it if needed. So what is a graph? Okay, so graph basically, first let me give informally. It has vertices and edges. Consists of vertices or nodes. Sometimes people call it nodes, connected by edges. Okay. I can give the formal definition, but first let's maybe see a couple of things. So here I just show you a picture of a graph. Okay, so what is does everyone see the picture here? So these are the nodes here. These are the nodes, and they have been connected by edges. Not that there is an edge between every pair of nodes, right? So between this one and this one, there is no edge, no direct edge. So these are supposed to be edges. I have not defined it, by the way, just take it informally. Probably it is familiar to many of you. If not, just take it informally. The proper definition can be given, but it's more important to visualize it actually. So these things, these little circles are the nodes or the vertices. And these lines connecting them are the edges. Now it's not something very specific, like it's really a combinatorial object. It is not that how I write this here is not important. Whether I use a straight line or a curved line, all those are not important. And you see that this edge and this edge seem to intersect, but there is no node here. You have to imagine this edge as going somewhere up here and this one going down here. Okay, so there is no node here. So this is an example of a graph. So a lot of relationships in the world can be captured in with the notion of graphs. That's why it is very important. For example, Facebook network or your just social network. People, you have a collection of people, and let's say those people you mark as nodes, okay, and you put an edge if two people are friends. So that gives you a graph, right? So this is what a graph is: collection of vertices with edges, which may be some relationship, okay. It can be whatever kind of relationship. So you connect to, so friendship graph is one graph, or you could have a collection of vertices which consists of some movie actors, and then you put an edge between them if they have acted in the same movie. That is a graph of collaboration between movie actors, etc. So lots of such things can be there. So these are here is another example of a graph. Usually all my graphs will have vertices which are labeled. Okay, so in the first example I showed, they were not labeled, but always think of the vertex set as a labeled set. So here all the vertices are labeled from 1 up to 20. Okay, and you see this is a different kind of graph structure. Any questions? Was there a question? I heard something, so maybe not. Okay. Okay, so these are examples of graphs. There are lots of graphs one can draw. So let me draw another one. So this is an example of a graph. This is like a Z2 lattice. So you can draw however big you want. So this is an example of a graph. Okay, so there are many graphs depending on what you want to capture, it is there. So how would you, if you want a formal definition, if that makes you feel any happier, so let's try to define it. What is a graph? It is informally that is that. So what is it? So there are two ingredients. So graph G consists of two things, V comma E. Okay, so where V is just any set. So we call this vertices. Okay, and E, it is a, I will write it, a symmetric subset of V cross V. Okay, V cross V, you know, V cross V is the set of all ordered pairs. U comma V, U and V are elements of this vertex set. So that's what V cross V is. A subset of that we understand. What is symmetric? Symmetric means if UV is an element of E, then VU is also an element of E. Okay, so what are we saying? What are we talking about here? What this means is that in these graphs, so let us say here you take two vertices, 19 and 17. Okay, so there is an edge between them. The edge is not 17 to 19 or 19 to 17. Both. It's an undirected graph. So that's what this idea is. That the edge is not from one vertex to another, but between two vertices. So sometimes it is important to have the other notion, but for these lectures, I will stick to this kind of thing. For example, you could have a graph which consists of a lot of people, and you put an edge from U to V if U is the father of V. Okay, so that becomes a directed graph because U is the father of V. Then there's an arrow from U to V, but not from V to U. That is a different kind of graph called directed graph, which I am not considering. In my case, it will be some mutual relationship like friendship, have acted in the same movie, that sort of thing, which is a mutual relationship. So if U is related to V, V is related to U. You can phrase this E, you can write E if you like, if you know what the notion of a relation is in mathematical terms, then E is a symmetric relation, actually. That's what it is. Okay, so this is what an edge is. So these are called edges. Okay, so elements of E are called edges, elements of V are called vertices. So we typically, so just to draw one picture here. So let's say our vertices are labeled 1, 2, 3, 4, and 5. So maybe you have something like this. So this is a graph. Okay, maybe you have. So this is a graph. So one of the things that I'm going to assume all through, so by and large, we will stick to the following thing. So let me put down some standing assumptions. It's not that people don't study otherwise, but in these lectures, I'm going to do, these are my standing assumptions. So they are standing. Okay. So what is the standing assumption? One is V is finite. So we just say that the graph is finite. So the vertices, the number of vertices and edges are finite. Okay. So that is an assumption. Okay. That is one thing. So it will always be like this. One can also imagine an infinite graph. What is an infinite graph? So for example, here is an infinite graph. You take all the integers. So vertex set can be integers and edge set can be all. So because UV, so because of this symmetry, we often write. So because UV and VU are both there, instead of writing it, doesn't make so much sense to write it as an ordered pair. We write, because of this, we write the edge as, sometimes we can write it as an unordered pair, because if UV is there, VU is also there, and or UV, or we write it as UV sometimes, or we may write U adjacent to V. So we say U is adjacent to V means U to V there is an edge, or U to V or V to U both the same, UV form an edge. So all these notations are used to say that UV form an edge. Okay. So an example of an infinite graph is here, an integers, and E can be the set of all edges between n and n plus 1. So I can have 0, 1, 2, minus 1, minus 2, and so on. So this is an infinite graph, and the set of edges are n, n plus 1. So this is an infinite graph. So we will not be considering, a lot of things I say can also go through for that, some things, but for there's no need to break our heads about that. There's a lot of interesting stuff to say about just finite graphs. So we'll stick to finite graphs. Okay. Second point, I will assume that there are no loops. So I said E is a symmetric subset of V cross V. So we assume that is no edges of the form UU. So you can also put an edge between U and itself. Okay, when I said two actors, you put an edge between them if they have acted in the same movie. Surely any actor has acted with himself or herself. So you could also put an edge between them. So it depends what you want to capture. For example, there could have been an edge like this. So 2 is connected to itself, maybe 4 is connected to itself, maybe 1 is not connected to itself, 1, 3, 5 are not connected. So those would be loops. Okay, so this is what is called a loop. So this is a loop. So we assume no loops. Okay, so just for simplicity, we remove that. Edges are between distinct vertices. So edges are going to be between distinct vertices. Okay, so that is the idea. Okay, so this is the notion of a graph, and as I showed, here are some examples of graphs that we see. So for example, a graph, there are names for various things. So this type of a graph where you see this is called a tree. Okay, I will define it properly later. It is somewhere where you don't have a cycle. So for example, here you can go from this vertex to this vertex to this vertex to back. You can loop around, not a loop as I defined it, but you can have a path which goes and comes back. But here you cannot have, in this, you cannot have any path. You have, if you have to go from this vertex to itself, wherever you go, you have to retrace the steps back to come back there. Okay, so this is called a tree. This is a general graph. Okay. Any questions, comments, or anything so far? I mean, this is the basic notion that we have.
Sir, there will be no multiple edges.
Yeah, so no multiple. So as I said, I got E as a subset of V cross V. So that means anything will occur only once or not at all. No multiple edges either. So more general notions can be allowed. So like you said, multiple edges can be allowed sometimes. Very generally, there is another notion that is very important and useful. We will take in the tutorials, you can explore a more general object. So let me just write that here. But in the lectures, I will stick to this. In tutorials, a more structure would be a weighted graph, which consists of three things. There is V, there is E, and then there is W. Okay, so V and E are as before. Okay, V is a set, E is a symmetric subset and all that. And W is, you don't simply have edges, you have a function from edges to positive real numbers. Okay, so a weighted graph might be like this. So let's say 1, 2, 3, and 4, and on each edge there is a weight. So there is a 0.5, 0.2, 1.7. So always the weights are assumed to be non-negative, but these are the weights. So that is a weighted graph. That also can be considered. So we'll not consider it. It's a good topic to explore in tutorials. Everything I say can be carried over to the level of weighted graphs. But why complicate things if it doesn't necessarily? I mean, it adds, it gives more power, but the understanding is not improved by it going to a more complicated setting. So I will stick to the simpler setting. So in lectures, we stick to unweighted graphs. So unweighted means G is V comma E. Or you can also think of it as a weight, which is taking two values, 0 or 1. W of E is 0 means no edge, and 1 means edge. Okay, so for any edge, instead of a general graph can be thought of as a weighted graph where the weights are 0 and 1. So if there is an edge, this weight is 1. If there is no edge, there is no, I mean, it's 0. Okay, so that's another way to think about it. But as I said, in the lecture, you stick to this basic notion where we have a vertex set and an edge set. So your question of multiple edges can be captured under weights. For example, if you talk about that example I gave, you take movie actors and you put an edge between two of them if they have acted in the same movie. Now, you can put more information in this if you put not just if they have acted in the same movie, but on the edge you place
Sir, excuse me, sir.
Sorry?
Sir, you have said weight W is a function from E to 0, 1, right? And
Not always. In case of
yes. But if there is no edge, then how can WE be equals to 0? Means there is no edge.
Okay,
Means
there
it is
is
not belongs to E.
Okay, so if you want, right, in the case of this, if you want, instead of this, you think of as a function on V cross V itself. A priori, everything is an edge.
Okay. So
Even
complete
here,
graph.
if you want to take V cross V. You can take all possible edges, but you give weight. Weight 0 means no edge. But you have weights, you have weight, one means edge. Okay, so yeah, you're right. That is a better way to say it. Otherwise, it's confusing. Okay? If E belongs to the edge set, then we call the weight as graph. Okay? There is some bit of noise for some reason, some clicking noise. Hello? Okay, I don't know. There is some noise, but okay. So let me go back to this. Yeah, what was I saying? So in the case, in the example of that, so somebody asked about multiple edges. In the case of if you take movie actors and you put an edge between two of them, if they have acted in a movie, you can put more information on your graph by putting not just if they have acted in the same or not. You put how many movies they have acted in common. Okay, so then between if two actors have acted in a lot of movies, that has a lot of weight, and they have acted in only one movie, the weight will be 1, and so on. So there the weights will be integers. If you want, when the weights are integers, you can think of it as so many different edges going between them, each edge corresponding to one movie, right? So it's just complicated to write. It's easier to write one edge and put a weight on it to denote the multiplicity. Okay, so this more structure is there, but we stick to this point is important. We stick to unweighted graphs in the lecture, and these assumptions are also going to be made always. That makes it simpler. Any questions so far about the basics of this? Okay, so some examples of graphs are always good to keep in mind. So there are various examples. So let me just, I already showed you some. Let me show you one more, a very important one, which we'll come to. So complete, So complete graph. So complete graph means what is here. So you see, complete graph is that special graph is a particular example of a graph where you have some number of vertices, in this case 7, and every pair of vertices is connected by an edge. No loops, but between every pair there is an edge. You see, right? You take any two vertices, there is an edge. That is called a complete graph. So let's write down just for the later reference. So let me write here some examples. Kn is the notation for complete graph on vertices. Vertex set is, when I write square bracket n, I mean the set 1, 2 up to n. Okay, you take the set 1, 2 up to n and complete graph. So example, I showed you already. So but n equal to 4, there will be 4 vertices and they will be labeled 1, 2, 3, 4, however you want to label. Between every pair, there is a between 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4, and between 3, 4. So this is a complete graph. Okay. So there is also complete bipartite graph. With parts, I will write and then I will show you the picture. Parts containing m and n elements. So here, this is K4. So let's write an example here. So let's say m is 2, n is 3. What it means is there are two, the vertex set consists of two parts, okay, which we usually write like this: m on the left side, n on the right side. No edges between themselves or between themselves, but across it is complete. So every vertex here, so maybe we can call it 1, 2, 3, 4, and 5. They are the vertices. 1 is connected to all these things. 2 is connected to all these things. So this is a bipartite graph. This is K2, 3. Okay. So there are many other graphs. So like, so grid graph. So I showed you some examples here, grid graph and other things. Let me just tell you the notion of a tree, or a tree is a graph connected graph without cycles. I have not introduced what connected is. One can define it more precisely. You see, connected is, so for example, nothing in our graph says that all things have to be connected together. So for example, so if I take a graph like this, if I have so this is a graph, this is not connected. Okay, because you see, in the sense that this part is separate from this part, right? So what is the precise notion? So one can define a path on a graph means you go along edges. So let's say you start from 1, you can go to 2. Okay, think of walking along the edges. Okay, so think of these nodes as these edges as streets, and these as the intersections of streets, okay, of roads. So you can walk from 1 to 2, then you can walk from 2 to 3. So let us say you have one more vertex here, 6. So you cannot directly go from 1 to 6, but you can go from 1 to 3 and then 3 to 6. But there is no way you can go from 1 to 4. Whatever you do, you can never get to 4 without jumping. So it's not connected. So connected means you can go from any vertex to any vertex by walking along the edges. Okay, so I will just leave it with that informal notation. Can walk.
No, sir.
1 second, let me finish. From any vertex to any other vertex by walking along the edges. Along the edges. Okay, so that is what connected is. And I let me just finish it. I'll take your question. Just sorry, 1 second. So without cycles means it is what I described earlier. Okay, so you cannot come back. So without cycles means okay, I will define that later. Okay, so yeah, what is the question?
Yeah, actually, you said that we can go from one edge, one vertex to the other vertex. Whether the edges or vertices can be repeated, or is there any restriction on that?
No, you can repeat if you want. That will not change which vertices you can go to. Okay. In general, when I say path on a graph, you are allowed to visit. So for example, you may go from 1 to 2, 2 to 3, 3 to 1, and then go back to 3 and then go to 6. That's just a roundabout way of going to 6.
Okay, so we can repeat. Yeah. Okay.
Yeah, but for this definition, it does not make a difference, because if you can go from one vertex to another by repeating, you can also go without repeating. Okay.
Yeah.
So
Yeah.
that for this, but in general, yes, path means you are allowed to repeat.
Okay, thanks.
So so let me define cycle. Okay, so because this notion will come again, a cycle is a sequence of vertices V1, V2, Vk such that V1, V2 is an edge. So V1 is adjacent to V2, V2 is adjacent to V3, and so on. Vk minus 1 is adjacent to Vk, and then it comes back to V1. So Vk is adjacent to V1 again. Okay, so that is what, so for example, 1 to 2 to 3 to 1. Okay, 1, 2, 3 is a cycle because you go 1 to 2 is an edge, 2 to 3 is an edge, 3 to 1 is an edge. So all those are edges. So a graph without cycles and connected is a tree. Connected is important. For example, if I just take so this graph is not a tree, has no cycles, but not a tree, because it is not connected. So what is correct? What is a good name for such a thing? It's a collection of trees. This is itself a tree. This is a tree. So this could be called a forest. That's what it is called. Okay, it's called a forest. Okay, so those are some basic notions of graphs. I'm going kind of slowly. If you want, you can also tell me to go fast. That's up to you. I mean, so I am assuming I don't know what the backgrounds of people are. If it gets too slow, I mean, maybe Rajesh can tell me. I don't know what level it is, but it's okay.
It is
Rajesh?
a heterogeneous group consisting of students, research scholar, and also teachers.
Okay, so it's okay this space. I mean, so it's all right.
It's okay.
Yes, sir.
Okay. Okay. So this is the notion of a graph. Okay. So now let's come to, this is a workshop in linear algebra, right? So somewhere there should be matrices and so on. So where are matrices? Okay. So there are some matrices associated to graphs. So let's come to that. So let's take a graph G equal to V comma E. Remember, V is vertex set, E is edge set. Everything is assumed to be finite. No loops, no multiple edges, no weights. Okay, so this is what it is. So there are, so just as an example on the side, you can keep this. I will show you on the program. I was showing this program here. It's always useful to have a computer program to draw examples and other things. Because you can see, you can make by hand, I can only show you small examples. On the computer, I can show you bigger examples. So I will show you examples on the computer program. Okay, so that's the Mathematica that I'm using there. But pretty much every software, good software, mathematical software allows you to draw graphs and so on. Okay, so first one is what is called the adjacency matrix. What happened? It's not writing for some reason. I don't know what happened here. Okay. Adjacency matrix is the following. It is so let's for simplicity, yeah. So it is a matrix which is V cross V matrix. So the rows and columns are indexed by vertices. So that's why I write V cross V. If you like, you can always assume V is 1 to n. Vertices are always labeled. Okay. So if you like, you can take V to be 1 to n. If it confuses you to write what is the meaning of V cross V matrix, when V is 1 to n, all I mean is it's an n cross n matrix where the ith row is indexed by the ith vertex and j is indexed by the jth vertex. And what is this Aij? Aij is just indicating whether or not I and j are connected by an edge. So it is 1 if I is adjacent to j, and 0 if I is not adjacent to j. Okay, so that is here I and j form an edge. If I and j form an edge, you put a 1, otherwise you put a 0. Okay, so that's what an adjacency matrix is. It tells you which vertices are adjacent. So let's go over here. Let's take a simple example. So why so many? So let's take okay, so I wanted vertex labels. What happened? Okay, so let's take G to be this one. Okay, so G is this. Okay, so you see, is this with, oh, sorry, something is wrong. Okay. This is not what I wanted. No, this is not the way to label. Yeah, okay. So maybe somehow this is coming out labeled. So let me just use this, although this is a very simple graph. So here you have a random. So let's say G is this graph. Okay, so you have vertices labeled 1, 2, 3, and 4. You see this, right? I mean, is this program visible? I mean, is the on screen, is it clearly visible what is going on?
Yes, sir.
It is visible, right? Okay. So if this is our graph, then what is the adjacency matrix associated to this? If I write adjacency matrix of G, okay, why is it slow? For some reason it suddenly got slow. Okay, so what happened? See, one, so one, now what happened? Why is it labeling it like this? G is this, right? Okay. Okay, so if I, something is wrong about this. This is not the adjacency matrix of G. I mean, it's ridiculous. What is it doing? Okay, I don't know what happened. So let me go back to, sorry about that. So let me write my own picture. I must have made some mistake in the syntax. So let's take a simple graph here as an example on the side. So let's take vertices 1, 2, 3, 4. Okay, so this is my graph. Okay, so then the adjacency matrix will be, it will be a 4 by 4 matrix. Just for our reference, we can just put down here what the vertices are: 1, 2, 3, and 4, and 1, 2, 3, and 4. Okay, on the diagonal, there is going to be zeros, no doubt, because we are assuming no loops. There is nothing. On the diagonal, you will always have zeros. Now, what are the edges? 1 and 2 form an edge, so I put a 1 there. 1 and 3 don't form an edge, so I put a 0 there. 1 and 4 do form an edge, so I put a 1 there. Now 2 and 3 do form an edge, so I put a 1 there. 2, 3. 2, 4 is also an edge, so I put a 1 there. Now 3, 4 is not an edge, so I put a 0 there. Now on the other side, it's the same because our edges are undirected. 1 and 2 forming an edge is same as 2 and 1 forming an edge. So you see, I can just copy this. So this matrix is necessarily going to be symmetric. So this is the adjacency matrix of the graph. Okay, is that all right? Okay, so now let's introduce one more. So yeah, okay, so this is one way of capturing the relationship of the graph in a matrix. Okay, it's just a way of writing the graph, representing a graph by matrix. Because if I tell you the adjacency matrix, then you can recover what the graph is. You just label the vertices as 1 to 4, 1 to 4, and you just draw the edges according to it. You should give me a symmetric matrix, otherwise it won't be a proper graph. It won't be undirected graph. Okay, so what other thing is there? So one more type of, so let me, one most important object that we will be studying. This is the matrix that I am going to introduce now. It is called the Laplacian matrix. So this is also a V cross V matrix. But before introducing that, let me introduce a simpler one, degree matrix. Because that will be needed in the Laplacian. This is a D is V cross V, where you put what is DUV? duv is, it's a diagonal matrix if u is not equal to v, and it is the degree of u if u equal to v. Okay, so I have not yet introduced what is degree of u. Degree of u is the number of edges adjacent to u. You see how many edges are connected to u, that is what the degree is. Okay, so let's see in this example, let's write down in our running example, what is the matrix D? It will be a 4 cross 4 diagonal matrix. Okay, so it's a 4 cross 4 diagonal matrix. What is the degree of the vertex 1? Yeah?
2.
2, right? So what are the degrees? You can tell me. So degree of the vertex 2 is
3.
3, because it is connected to 1, 2, and 3. Okay, so there are 3 vertices it is connected, 3 edges coming out of 2. Whereas the degree of 3 is only 1, because it has only 1 edge coming out of it. 4 has 2 edges coming out of it, so that is 2. It is important that the labeling be followed. Okay, so you follow, I mean, so if your vertices are labeled 1, 2 up to that, then you should write it in the corresponding way. Otherwise, it will lead to some kind of permutation of these rows and columns. Okay, so that's what the degree matrix is, just a diagonal matrix with this. Now with that, I can now define for you the Laplacian matrix. This is crucial. This is the single most important object that we will be studying. Okay, so it's very important. So what is it? What is it? It is simply D minus A. Okay, so in other words, what you have here is, if the vertices are labeled, I will just write it like this, D1, D2, Dn, and minus Aij here. So let's do it in the specific example here, then we will see. So L in this particular example is, on the diagonals, we will have the degrees. So I just copy from the degree matrix. On the off diagonals, I have the A entries, but negated. So I put a -1, 0, -1, 0. Sorry, this is not 0. This is -1. -1 and -1 here. And this one is 0, 0, -1, -1, -1, -1, -1. Okay. So this is the Laplacian matrix. Okay, so it is a very, very important matrix. So just because it is so important, let me write here. Where, let me just write out the definition explicitly. LUE -1 if u not equal to v, but u is adjacent to v. And it is degree of u if u is equal to v. And it is 0 otherwise. Okay, so wherever on the diagonal you put the degrees, on the off diagonals you put -1 if they form an edge, and 0 if they don't form an edge. That's what the Laplacian matrix is. Okay, any questions about this?
Sir, L31 equal to 0.
Sorry,
L31.
Oh, should have been 0. Why? Oh, did I? Oh, sorry. Yeah. You're right. This should have been 0. Thank you. This was actually 0. It is, L is also a symmetric matrix, by the way. Okay, L is a symmetric matrix, just like A. All these 3 are symmetric matrices.
Sir, one question.
Any questions here?
Yes, sir. Sir,
Huh?
from graph A, from matrix A,
Yeah.
we can go for graph, but from
Yes.
D we cannot go because.
From D you cannot. Yes, that's a
But
good
for
point.
what about L, sir?
Yeah, because from L, if you ignore the diagonal, you already get A, right? L has all the information of A.
Yes, sir.
So if you just ignore the diagonal and negate everything, you get A. So you can go from L to the matrix.
And
From
then
L, you can
graph.
reconstruct the matrix. Yeah, sorry, the graph. From L, you can reconstruct the graph. Yes. Yeah, from degrees, you cannot reconstruct a graph. Good.
Okay.
Any other questions? So this we have associated some matrices. Now, one of the whole topic of my lectures is this, that these matrices have actual information about the graph. Okay, it looks like we have just put together some numbers in a table. Okay, just putting numbers together in a table doesn't make a matrix in the real sense, right? Okay, it does make a matrix in the definition. It's a table of numbers. But when you study linear algebra, there is a geometric aspect behind it. For example, eigenvalue. Okay, eigenvalue of a matrix has some deep meaning. Okay, so square matrix, if you have a square matrix, you can talk about its eigenvalue. You can talk about its column space. You can, but in this case, we have just put together numbers in a table. Does eigenvalue or column space, all these, do they have any meaning? Does rank have any meaning? Okay, it turns out that it is true that there is meaning, and a lot of graph properties can be captured by matrix properties of this matrix, which is the Laplacian, and that is the subject matter of my lectures. Okay, so that is what we are going to see. So we will see. Even today I will tell some things like that, but before that, let's see some very basic proper. So yeah, maybe so any questions so far? No. Okay, is there? Okay, then I'll proceed. Yeah, so what should I tell? Should I tell you an interesting theorem first, or I'm thinking what I should tell? So, okay, first let's do some very basic properties of Laplace.
Laplacian Matrix.
Yes.
لما أساسا lecture وإسنا
Sorry?
presentation ما يا GeoGebra
was
أصلا لك هي
I cannot understand. Did you ask a question? Hello? Hello? Okay, maybe somebody is unmuted. Okay, so basic properties of Laplacian. First, L is a symmetric matrix. Okay, so Lij is Lji. So if you want, you can always take V to be 1 to n. Okay, so let's write like that. Okay, it is symmetric. So, but I'm now going to tell something more interesting. So what is, let's look at what is, here is another point I want to tell. What is all this business of graphs? What is actually the whole business about? Graph is one way of capturing the notion of space. If you have studied some other forms of mathematics, you may have studied manifolds. For example, you have studied analysis, you have studied open sets, etc. If you have gone more advanced, you may have studied manifolds. That is also a way of capturing space. Okay, manifold is a way of capturing the notion of space. What points are closed, what points are not, etc. And graph is a discrete version of similar thing. Okay, graph is just a discrete version of the same. So anyway, so it's a very geometric thing. That's another way to think about it. I mean, it is a combinatorial object, but its analogy is with geometry. So how does it act on vectors? Okay, so by the way, so there, let me tell. So let f be a function from V to R. This is, we can identify with a vector. So a function on vertices can also be thought of as a vector f of 1, f of 2, f of n in Rn. Right? I mean, so what is giving a function? You have to tell the value at all the vertices, and I can put the vertices in order and write this as a vector. So I will constantly move. I can say function on vertices and vectors in Rn are the same thing. Okay, when your vertex set has n elements, functions on vertices are same as vectors in R. Okay. So let us look at how Laplacian acts on this. How does Laplacian act on it? What is the vector LF? LF of I. Okay, so what is LF of I? So you know how to multiply a matrix with a vector. So LF of I means you have to take the ith row of L and multiply the vector F, right? That's what you have to do. So this is Lij F of J. Okay, what is Lij? We have the formula here. For I equal to J, you get, when I is J, you get the degree of I. So you will get, let me just write di. Okay, so that's the degree of I. If you want, let me just write degree of I. Degree of I times, let's write d of I first. Maybe we have to write it many times. There is no point keeping on writing it degree. So d of I is the degree of I times f of I. That comes out. And what about the rest of them? Most of them are 0. Only those j which are adjacent to I will give you a -1. So you will get minus sum over f of j over j which are adjacent to I. Okay. So all those j, I mean this sum is over j. So I should put like this. J colon means I am summing over j, but only those j which are adjacent to I, this fj will get subtracted. Which you can also write a bit more simply. How many summands are there in this? How many summands are there?
Easy, sir.
Exactly di. So I can put this inside with, because it has exactly that multiplicity. I can also write f of I minus f of j. Okay, so that is one way to write. So what does LF do? If you have a function, what it does is it subtracts. You take the value from all the neighbors, you subtract from f of I, add up. Okay, in some way, if I were to divide by the degree, it is f of I minus, if I pull out d of I, it is f of I minus the average of the neighboring values. So you sort of, that is what LF does. Okay, LF acts like this. It takes the neighboring values and subtracts and adds it up. So for example, so this is how this acts. This is important. So in particular, if f is 1, so this is the constant one. So I just write with this font 1. Okay, it's the vector which is 1, 1, 1, 1, 1. That means a function which gives the same value 1 at all the vertices. Then L applied to the vector 1 will give me what? What will that vector be?
So 0.
If you take the constant vector and apply L, what will you get?
So the 0 vector.
You will just get the 0 vector. Okay, that's what it is telling you, because you're subtracting the neighboring values. Each of these things is 0. So LF of I is 0. Or if you want, you can notice here that the row sums are 0. Okay, the row sums are 0. Because it's symmetric, column sums are also 0. That's the same as saying this. The row and column sums of L are 0. Okay. All right, that's one way to think of it. L is kind of a, if you have seen what is, so for example, so here let me say one thing just in case you people are aware of it. So LF of I is 0 if and only if f of I is 1 over the degree of I times f of j over all j adjacent to I. Okay, so what it means is Laplacian applied to a function at a vertex is 0 means the value of the function at that vertex is the average of the values at the neighbors. Does this remind you of anything you have seen in mathematics? Function value is equal to the average in a neighborhood. Have you seen that sort of thing? Maybe complex analysis or somewhere.
Yes, sir. Cauchy integral form.
Huh?
Cauchy integral.
I could not hear. Can you say again?
Cauchy integral formula.
Cauchy integral formula, sort of, not exactly, right? Cauchy integral formula, it is related. Yeah, it's related, but something more specific. Have you heard of harmonic functions? Harmonic functions have what is called mean value property. Harmonic functions are defined, let's say, on the plane. The value at a point is equal to the average of the value in any ball centered at it. So this is the discrete analog of it. So we say a function is discrete harmonic because the value of the function is the average of the values at the neighbors. So this is the mean value property. So a function that has this property at all I will be called a harmonic function. Okay, or if it has at one I, it is called harmonic at I. So if you have not seen that notion, then forget it. But I thought some of you may have seen the notion, so I mentioned it. Okay, so let's come to one more thing. If you have a symmetric matrix, you can apply it to a vector. There is one more thing we can do. We can look at the quadratic form. Associated to L. Let's look at the quadratic form associated to L. What does quadratic form? Does everyone know what is quadratic form of a symmetric matrix? Can someone tell me what is quadratic form?
It is X transpose AX.
X transpose AX. So it takes a vector X and gives you the number X transpose AX. Okay. So X transpose LX, which we can also write, if I like to write without not as vectors, but in terms of this, I can think of it as LX inner product X. Okay. Is that okay? These two are same, right? LX inner product X is X transpose LX. So this is what the quadratic form is. So let's look at LF. Let F be a vector, or in other words, a function on vertices. A function on vertices can be thought of as a vector on in Rn. As I wrote earlier, I am writing it again so that you get used to that notion. This is a function on vertices. So let's calculate LF inner product F. But what is it anyway? If you write this, it is sum over I and j, Lij, xi, xj. Right? I mean, if you have ever done this, it is very simple. You can work out it is Lij, xi, xj. If you don't remember it, do it. Okay, so this will be sum over all I and j, Li comma j, and then f of I, f of j. Now, what is this? Lij we know, right? So when I equal to j, what do you get? So let's separate the I equal to j parts. Here I will get
Dij.
di. No dij, just di. When I is equal to j, this will be the degree of that common vertex, I or j, whichever you want to call. I am calling it I. And you will get f of I squared. Then you get a sum over all I and j, which are adjacent, right? Because what do we get? Whenever you have two vertices which are adjacent, we have a -1. So we will get Lij is -1. I get a sum over all plus I and j, which are edges of f of I, f of j. Okay. Is that okay? It depends on how you interpret this. So ij and ji are interpreted separately here. Okay. So if I don't write this like this, but if I write it like sum over all sum over all edges, then I should put a factor of 2. Meaning I and j and I come twice, because in L, the edge 1, 2 will come here as well as here. It comes 2 times. So if you are summing over, it depends on what you mean by this sum. If the sum is over all edges, then you have to take a factor of 2. Okay. So now what shall I do? Now let's rewrite it like this. I say that this is the sum over all possible edges. So this sum is over all edges. Okay, so same for this over all edges. Now, what I want to do is I have minus 2 f of I, f of j is there. Okay. Now I will take 1 f of I square from here, and I'll take 1 f of j square from the jth term. Okay, so I have a term I connected to j here, right? Now I take 1 f of I square and 1 f of j square. Is this okay? I mean, because how many times f of I square comes? All the edges adjacent to what I do is f of I square, let's say the degree is 3. Then I send it once to each of the edges which is connected to this. Sorry, there is a little bit of noise. Can you mute yourself? Hello? There is a bit of noise. Please, I mean, if you are, whenever you want to ask questions, please do unmute, but otherwise keep it muted. Okay, what I am saying is that the degree of I is the number of times, number of edges adjacent to I. So I will send f of I square once to each of those edges. So this is exactly equal to this. Okay, so if you want, think about this. If it's not clear, think it's a good point to think about. If it's not immediately clear, you can go and think about. But now this is in a very nice form. What does this give us? What is this? This is the sum over all edges of f of I minus f of j whole squared, right? Because that's the square, f of I minus f of j squared. So what is LF inner product f? It is the sum of squares of the differences in the f. So in a sense, what it is telling us is LF inner product f measures how much f differs on adjacent vertices. So if f is the constant function, then f of I equal to f of j for all I adjacent to j. So this gives me 0. Okay. Otherwise, it will give me something. So that is what the Laplacian quadratic form is. Any questions about this derivation? Okay, if this step is not clear, you think about it. That's a good way to do it. Now, can you tell me what do you learn about L from this formula?
It is positive semi-definite.
L is positive semi-definite because LF inner product F. Therefore, LF inner product F is greater than or equal to 0 for all F, which implies that L is positive semi-definite. I'll write PSD. Okay, it is positive semi-definite. Is it positive definite?
No, sir.
No, sir.
Not positive definite. Why?
0 is an
Zero is an
eigenvalue.
eigenvalue.
Sorry?
0 is an eigenvalue. Always.
Did not hear.
0 is its eigenvalue, sir.
How do you know?
Because all one vector is always there as an eigenvector.
Yeah, so you can also see it from here because L1, we already saw L1 is 0, but L1 inner product 1 is also 0 for that same thing, same reason. Okay, so many ways to see L is singular because the row sums are 0, column sums are 0, or another way of saying it is that L applied to the constant vector gives you 0, so the kernel of L is non-empty, okay, not trivial. And another way to see is from the quadratic form, L applied to the constant vector inner product with itself is 0 because all these terms are 0. So it's not positive definite, but it is positive semi-definite. Okay, very important fact. Okay. So we will tell one couple of things. So this will come later. So, but just for fun. So you see, one thing already happened, which is a bit surprising. What we did was we had this notion of a graph. We just put together some numbers in a table and called it Laplacian matrix. But you see that matrix somehow has a very nice property that is associated to matrices, a rather deep and interesting property of matrices called positive definiteness. It is very important property, right? So this just table of numbers, suppose, is not just any table of numbers. it has some nice properties as a matrix. Okay. Its eigenvalues are, for example, non-negative. So later we will see, because now I want to go into a different topic, that, okay, so no, let's do one more thing, because it's a symmetric matrix. Now, what do you know about symmetric? What is the most important thing you know about symmetric matrices?
All eigenvalues are real.
Real eigenvalues.
Real eigenvalues, very good. Anything more?
Orthogonal eigenvectors.
Orthogonal eigenvector. So what is it called?
Spectral theory of
The whole thing. If you put together all this.
spectral theory means
Spectral theorem. Spectral theorem for real symmetric matrices tells us that we can write L as lambda 1 F1 F1 transpose plus lambda 2 F2 F2 transpose plus lambda n Fn Fn transpose. I don't know if you have written it in this form. This is one way to write, where so the first eigenvalue is actually 0. So let's order the eigenvalues. Since we know it's positive semi-definite, the smallest is 0, but of course there can be more zeros also. So lambda 1 is 0, but lambda 2 is at least lambda 1, lambda 3 is at least lambda. We can order it like that. So these are the eigenvalues of L. And what is F1? Fk is an eigenvector for eigenvalue lambda k. So for example, what is F1? What is an eigenvector for 0 eigenvalue? We have seen that already, right? What's an eigenvector? The constant vector 1. But I want such that I want this to be an orthonormal basis. For R to the V, which is Rn in our case. If V is 1 to n, then that is Rn. So in that case, I don't want to write f as the constant vector 1 because it's not normalized. I should divide it by square root of n. So that the norm of 1 is n. So f1 norm squared will be 1. So you just divide by square root of n. So this is what the spectral theorem tells us, that L can be decomposed in its eigenfunctions and eigenvalues. It can be written as a sum of projections. It's also positive semi-definite, so the eigenvalues are non-negative. And we have an orthonormal basis of eigenvectors. Okay, so it's an important, most important fact about matrices, so real symmetric matrices, the spectral theorem. Now, yeah, what did I want to tell? Yeah, so okay, all this is fine, but what does L tell us really about? What does L tell anything about the matrix actually? I mean, about the graph. Our interest is in the graph. We want to study graphs. What is the use of this matrix? That is what the whole topic is. So this is what we are doing. This is called spectral graph theory. The spectral properties of L, meaning eigenvalues, eigenvectors, contain a lot of information about the graph G. Okay, so we will see that. But for now, let me state one thing. So as an easy fact, here is an easy teaser. So this always for me, I will not write any further. Always the notation will stand. L will be Laplacian, lambda is will be its eigenvalues ordered in this way and so on. Okay. And Fis will be the eigenvectors and so on, unless I tell otherwise. So one of the questions about a graph is it connected or not? I showed you an example of a disconnected graph, right? Here is a graph which is not connected. Here is a graph which is connected because you can go from any vertex. These are all connected graphs. So one of the simplest graph properties, this has nothing to do with matrices, right? So an interesting property about a graph is it even connected? So one of the ways it works is, for example, in social networks. Okay, so you are maybe you are on Facebook and maybe I am on Facebook. Is there a sequence of friends such that you can go to your friend, your friend's friend, your friend's friend's friend, and get to me? Is it possible, or are we not? Is it not possible? That's the question of connectedness. Okay, so here is a very nice property. I say G is connected if and only if lambda 2 is strictly positive. Okay, so the connectedness, which is a nice graph property, here is a graph property, and here is a spectral property. Okay, a graph property can be captured by a spectral property. This is an if and only if thing. Why is that so? Okay, why is the connectedness of a graph equivalent to lambda 2 equal to 0? So a more general thing which I will leave for the tutorials is the following. More generally, the number of connected components of the graph is equal to the multiplicity of the 0 eigenvalue. You look at the multiplicity of 0 as an, so example, if lambda 1, lambda 2 up to lambda 5 was 0 and lambda 6 is positive, that means the multiplicity of the 0 eigenvalue is 5, in which case the graph will have exactly 5 components. So if lambda 2 is positive, the multiplicity is 1 and there will be 1 component, so G is connected. Okay, so this I will leave for you to think as exercise. Maybe this one we will quickly go over. Why is G connected? Okay, let's go one way. If G is, let's say if lambda, yeah, either way. So can you show either way? Can anybody give me a suggestion? G is connected implies lambda 2 is 0, positive, and lambda 2 positive. Or if G is not connected, so let's do that. Maybe that is the easier one. Suppose G is not connected.
Yes, then it will have at least 2 component.
Okay, so want to show, this is the question, lambda 2 then is 0. This is what we want to show. Okay, why do you say that? If G is not connected, why?
Then G will have at least 2 component, otherwise it will be connected.
Okay.
So let's say the 2 connected components are G1 and G2.
Yes. So let's have an example here in front of us. So here is a disconnected graph. This is G1 and this is G2. Okay.
Yes.
Okay.
Let's say G1 has n1 number of vertices and G2 has n2 number of vertices.
Fine.
Now consider the vector which has all the functional value corresponding to all the n1 vertices equals to 1.
So you put 1 on all these vertices and 0 on these.
Yes.
Okay. So if you put 1 on all these vertices and 0 on this, L applied to that will still be 0. Right? Why is that? So if we accept that, if we take we don't have to take 1 everywhere. So the suggestion is, so who is speaking? Sorry, I didn't see the
Somiran.
Soumya?
Somiran.
Okay. This one is, so if you put 1 on these and 0 here, you see the point is there are no edges between G1 and G2. So if you look at the quadratic form, for example, LF inner product F will still be 0 because for all edges, f of I and f of j are equal because there is no edge from G1 to G2. Within G1, F is constant. Within G2, F is constant. Similarly, you will get one more vector, which is 1 here and 0 here. So you get two linearly independent vectors, which are this. So that is the proof. Very good. So that's the proof because for each connected component, if G hat, if f of I is 1, if I in G hat, and 0 if I does not belong to G hat, then LF inner product F is 0. Okay. So what if G is connected, then lambda 2 . So I'm just writing the same thing in contrapositive form. So this is the question. G is not connected. Okay. Again, you can look at the quadratic form. For what f can this be 0? Okay, that is the question. That will tell you how many multiplicities are there of 0 eigenvalue. When can this be 0? This is a sum of squares, right? So for this to be 0, all the elements have to be 0. So the only way LF inner product F is 0 if and only if f of I equal to f of j whenever I and j form an edge. Okay. So now suppose there is a second eigenvector, then I am saying that it must necessarily disconnect. So if you have a non-constant vector, can this ever be 0? If the graph is connected, think of a connected graph and suppose f is not constant. Then there have to be two adjacent vertices where f of I minus f of j is not 0, right? And then the sum of squares will be strictly positive. Okay. So maybe if this is not fully clear, finish up in the tutorials. So left to tutorials. Okay. So if, because I want to say one more things and end it. I had planned to say other things, but it's okay. Going slow is not a problem. But give me feedback. If you feel it's going too slow, then I can speed up a little more tomorrow. But I will, if this was not fully clear, I kind of gave an indication. If it's not clear, it can be discussed a bit more in the tutorials. This point as well as this point. It all comes from the quadratic form, if you like. Okay. Okay. Any questions so far? Okay. So now let me go for something which is almost magical. Okay. So this Laplacian matrix tells us something very interesting about the matrix. Okay. So this subject so let me tell you what spanning trees of a graph are. Okay. So let's take a graph G. So let's have an example on the side. Okay. So what is a spanning tree? I want to talk about a spanning tree. Is I write subgraph. So there are terms I use which I will explain in words. Subgraph of G containing all the vertices and having no cycles. Okay. there are three conditions. So subgraph means you just have to take, subgraph containing all the vertices means you have to take all the vertices, but you can drop some of the edges. That's what it is. Okay, you can drop some of the edges, but all the vertices have to be there. But it has to be a tree. So it having no cycles, but it should be connected. Okay, so let's do example here. So what are spanning trees of this? So for example, if I take 1, 2. So this is a graph which contains all the vertices here, right? But it contains no cycles and it is connected. So this is a spanning tree. Can you tell me one more spanning tree?
Yes, sir. 4 to 1, 1 to 2,
One.
and 2 to 3.
1 to 2, 1 to 3, 1 to 4. Star.
Okay. 1 to 2, 1 to 3.
1 to 3, 1 to 4.
Okay, so that is also possible. Any others? Are there any others? So here you see, if I drop the middle edge, this one, I have a square, which is not a tree because it is a cycle. So if I drop here, I dropped one more edge, I could drop any of the other edges. So I could also do this. Or I could drop this other one. Did you understand? These four, I just take that square part, I drop the middle edge here, diagonal edge, and I drop one of the other four edges. So I got 4 of them. Any others?
Sir, 1, 2, 2, 3, 1, 3, and 4, 3.
Sorry, 2, 3, 4,
2,
3?
3, 4, 3, 1, 3.
Okay, so a star in the other direction. Right, so that's what you mean.
2, 1, 3, 4.
2, 1, 3, 4. Which one is it not here?
No.
Okay. So you are saying, you are right. So if I keep this edge, then I could either take these two or I could take it like this. Or the other way. I could take it like this. Is that okay? Any other? How many did we get? I mean, I am not sure if we got all. Have we missed any? So if we drop this edge, then we have to drop one more edge. So these are the only 4. If we keep this edge, then it seems to me that we have got all. So there are a total of 8, maybe. So does anyone see any other? So a very important question turns out to be how many spanning trees? So in some sense, trees are the simplest graphs, and how many different spanning trees are there in G? That is a measure of the complexity of G in some sense. Okay. So how many trees? So a big question is how many spanning trees does a graph have? Okay. Now here is an amazing idea. So this is a theorem. You see, as you see, even in this small graph, it's not so easy. I mean, counting is very difficult, right? Counting can be very difficult. But there is this amazing theorem of Kirchhoff, which says that number of spanning trees of G is the determinant of L hat. What is L hat? L hat is the matrix L after dropping one row, one column. So if I take determinant of L, what do I get? Determinant of L is 0 because L has a 0 eigenvalue. So there is no point taking determinant of L. You have to drop the matrix, drop one row, one column, and then take determinant. Then you get. So let's say for this graph, what is that Laplacian matrix? So let's see it in this. Let's work out this particular example. What is the Laplacian matrix here? So the degrees are 3, 2, 3, 2. And 1 is connected to 2, 1 is connected to 3, 1 is connected to 4, 2 is connected to 3, 2 is not connected to 4, 3 is connected to 4. So I have all this. This is 0, minus 1, minus 1, minus 1. Okay. So this is the matrix, right? So let us just go quickly to the computer and do this. So let us say L is, what was the, do you remember what was the first row? 3 minus 1 minus 1 minus 1. And what was the second row?
Minus 1, 2.
And then?
Minus 1, 0.
0. And the third row?
Minus 1, 3, minus 1.
Minus 1. And the last one is?
Minus 1, 0, minus 1, 2.
2. Okay. Let's just see, is it? Okay, it is this one, right? So if I do determinant of L, I of course get 0. But what I want is, let's say we drop the last row and last column. Okay, so I just drop the last row, last column. So I take first to 3 rows, first to 3 columns. Why is it taking so long? It's a very trivial calculation. 8. You see, this determinant gives you the number of spanning trees. It's almost magical, right? I mean, so why Laplacian matrix has this information hidden inside it? So one of the corollaries of this, which I will mention now in the last remaining 2 minutes, is a very famous theorem of Cayley.
Would work, or like we have to drop the ith row and the ith column itself?
Okay, that's a good question. Let us see.
It's like, what if we drop the first row and first column or something?
Okay, let's do this. So I drop the first, last column, for last row. I take first to third row, but I drop the first column. So you get minus 8. So up to a sign, it is okay. It doesn't matter which one you drop. Okay. You can drop same row, same column, you will get 8. Otherwise, you may get minus 8. But otherwise, it's okay. You can try it. You can play with it. But the idea, I mean, even if it was dropping the same row, same column, it's magical that it gives you something. So here, what Cayley tells is...
Can you give some intuition as to why this is happening, or like some sort of a rough idea?
We will prove it. We will prove it next time. We want to prove it. It's a great theorem. We want to prove it. I was thinking that I would be doing it. That just shows me how poor my judgment of my own timing is. But we will do it next lecture. No problem. But let me mention one interesting corollary of
No,
this.
my question is just an intuition, or like how we can see it or something, not the whole proof I'm asking.
Well, I don't know. Maybe you can think about it. Can you think of any intuition at all for this?
No, I find it quite surprising. Therefore, I'm asking.
Right, right. So maybe you think about it for a day. So you'll get the proof tomorrow. Yeah. So proof is not same as understanding, but we'll see. I don't have a very simple intuition to give you, to be honest.
Okay, thank you.
It's 11 o'clock.
So total number of trees with labeled trees with n vertices. If we ask this question, Cayley had considered this question: what is the total number of labeled trees with n vertices? When n is 3, I can have this 1, 2, 3. I can also have 1 here and 2 and 3 here, or I can have 3 in the middle. But all the rest are same, okay? They are all the same. So there are only 3 such things. So number is 3. So what is the total number of labeled trees on n vertices? The answer is n to the power of n minus 2. And this will follow from Kirchhoff's theorem. We will see that. But now I'm out of time. So let me stop here. If there are any questions, I can take, but we can stop here and we'll resume next time with the proofs of these theorems. Okay.